Hello everyone, and welcome to the chapter walkthroughs for From Social Science to Data Science by me, Bernie Hogan. This is chapter 14, Introducing Geographic Information Systems. In this chapter, I'm going to go through some of the basic concepts of GIS and of just map coordinate systems. We're going to install and then make use of the Python Spatial Analysis Library. We'll do that using some maps, including one of the default maps that's in there, as well as some maps that we've been able to access ourselves, pulling from the web, and with some data that I've also pulled from the web. We'll see how that gets merged in and visualized both at the national and subnational levels. It's not going to get too far into the actual analysis of geographic data, but I hope that what this does is give you the tools that you can use for your own work, and you can see then how you can link that in with other work that you've done within the other chapters or in your own Python explorations. So to get started, we're here at the learning goals here for today. We're going to appreciate how maps can convert locations into in space into a coordinate system. We're going to see how to use GeoPandas to create a map of the Earth. We're going to detail that map using a choropleth, which is a really popular type of mapping visualization where different areas, or usually in this case countries, will be colored slightly differently. We're going to make a GeoDataFrame with our own points, which is, we're really just going to use one point, but we're going to show how that can be done so that you can think about how to make your own GeoDataFrames rather than just use ones that are available. And then we're going to make a map at the subnational level using GADM shapefiles and OxCOVID data. GADM is a place online for administrative data, so it tries to consolidate all maps on different levels from counties and provinces and states up to nations. And OxCOVID data is a data set that has been used in the past to consolidate a whole series of multi-site data or multi-source data on COVID around the world, including data on infection rates across countries, as well as data on lockdowns and all sorts of stuff. In this, we'll actually be using a static version that I have already pulled from the OxCOVID dataset, and which is made available inside the repository for this course. So if you've downloaded everything through the GitHub in order to get here to chapter 14, then you should be good to go for the data that you'll need for this course. But you might not be good to go in terms of the install. We'll get to that in a bit, but first let's have a look and have a think about geographic information systems and mapping more broadly. So perhaps the key important difference in geographic information systems is between space and place. Now, space is a notion of any sort of 3 dimensions that we can attach a coordinate system, or sometimes 2 dimensions we can attach a coordinate system to. And place refers to the sort of cultural or sociological conventions to whatever is in that coordinate system. So generally we're talking about the Earth, and so the Earth, of course, we would say it's a place because we've named it Earth, but it really is just a planet that occupies some space in space. But what we've done is we've been able to superimpose coordinates over that Earth, and that allows us to mark where some things are relevant. We call them places. Now that gets, of course, really complicated and political and territorial, as those places end up being specific borders around countries, around territories. Of course, those borders can be contested, and even the data about the places themselves can be contested. We can investigate how there might be more or less data on a particular platform that is indicative of a country. I myself have done work in the past on which places on Wikipedia are available on which parts of the map, or which parts of the map, or which parts of the planet are well represented by data on Wikipedia. So in order to do stuff like that, we have to, first get a sense of how do we use coordinates, and then how do we map those coordinates onto the Earth. Well, we can think of the Earth kind of like an orange here, and sorry, I'm just in the way of that one right there at the top. It just says like a sepal, as it were. But so the Earth is like an orange. Like an orange, the Earth is pretty round. It's not perfectly round, but close enough. And it has poles. And we have this little diagram here. It's got a north and a south pole, and we could use these poles to arrange coordinates. For the Earth, these segments represent longitude. So 360 segments represent 180 degrees west, and then another 180 degrees east. So we can go around west to east or east to west, and that's 180. Now the reason why it's 360, it's just a convention, but it's a convention of it's one of a number, one of several numbers, which are like really easily divisible. And so you can chunk it up into a whole lot of little wedges or so forth. Now, as it turns out, an orange has 11 wedges, but in the Earth, here we are, we're sort of slicing them up into some smaller wedges right here. For north to south, the lines go latitude, and but these wedges across, they're the longitude, and there's one for each of them. And just like how an orange has a part of it that's kind of organized as we might say a top and a bottom, we can think of the same thing with the Earth as having a top and a bottom here. Now, depending on where you are on the Earth, you might debate and say that of course, Australia's on the top and so forth. But the point is that we just know that there is a pole here, and the Earth turns around that polar axis. It's also worth remembering then that we also have these longitude and latitude, and so thus anywhere on this sphere here, anywhere on this globe, it'll have a longitude coordinate and a latitude coordinate that we can use in order to pinpoint something on Earth. So now, in order to be able to visualize or map that in Python, I can certainly recommend using GeoPandas. GeoPandas is part of the Python Spatial Analysis Library. There's some other stuff that we'll see in there that's relevant. So things like Shapely, which is a way in which polygons are measured, and of course those polygons are going to represent parts on the map. GeoPandas is how we store the polygons as well as render them in a map. And we'll see a little bit more of GeoPandas in a minute. It's pretty much the same as Pandas, except it's going to have an extra column for geometry. Mapclassify is a really cool package. It does a lot of things in terms of how you manage distributions and split them up, and particularly when we're using choropleths, where we might want to say, these sets of countries under this amount, maybe it's a population or wealth or who celebrates Halloween or something, then they would they'd be one color, and then something would be a different color. Now, if it's a distribution, mapclassify will help us chop up that distribution in some smart ways. Now it says here, see the latest version of the Jupyter Notebook on the book's GitHub for suggestions on how on GeoPandas install. And that's exactly where we're going to go right now, because frankly, every year, the way that I install GeoPandas does tend to modify a bit slightly because it can be quite a complicated package, and it depends on a number of different moving pieces together. So in fact, let's have a look at that over here, and we'll just look at the geography chapter for a little bit, and as usual, of course, restart kernel and clear all outputs. And we can see on the side there what we're going to do, and there's not really much in the code on the headings before then. But then we get down to installing GeoPandas. Now, I'm going to recommend that we install GeoPandas in a thing called a virtual environment. Now, virtual environment is a place on your computer where you can run Python code, install Python libraries, but it stays broadly self-contained from the rest of your environment. So if you have something running in there, then it's not going to be noticed by something outside. So we might have another Jupyter lab running in a virtual environment. It'll have a different localhost port number. It might be port 8889, as perhaps we'll see now in a second. And you can make sure that your libraries stay separate from each other. Now, why is that relevant? Well, it's because Python continues to update, as does the PySAL library and pandas and so forth. And sometimes, if their updating is not in sync, you might inadvertently download a more recent version of Python that can't run some of these libraries, or a more recent version of pandas, and so forth. Virtual environments tend to correct that, although they can be a bit tricky sometimes to run and to link up together. But we're going to demonstrate this now in a minute using a virtual environment in conda. Now, there's two ways to create virtual environments with Python. One is with conda, and one is with just Python itself with the program called venv, V-E-N-V. But we'll see how to do this in conda because I found that it worked. So I have some commands here that you can use to do this. Now, the % symbol simply means the terminal prompt, and you should be pretty familiar with the terminal prompt by now. I assume that you'd end up running JupyterLab in the terminal. But I'm just going to bring one up right here, and this is that's the name of my computer. This is the name of my account, and this right here says base. Now, base means that we're just running on the plain default terminal that you would run if you type in terminal and then sort of select that. However, we're going to see some modifications to that now in a minute, so that's why I want to point that out here. Now, as it happens, I'm already running JupyterLab in a different terminal right over here, and so I'm going to want to shut that down now in a minute. perhaps, but you'll notice it doesn't even really matter because when we create a virtual environment, it's going to be running, in parallel to it. But the reason I'm going to want to shut it down is because I'm going to want to open up the very same chapter, this chapter right here, within the different virtual environment, within a different version of JupyterLab. Okay, so the first thing we're going to want to do is to create a virtual environment. And if you do this through Python, Venv, then it will create a folder underneath. But conda creates these as little archives that it stores within its broad Anaconda package. So you can generally create them anywhere. I'm going to do it within my home directory right here. And so here's the first code for that. Conda create, and I'm going to call it GeoEnv for now. And you'll also notice here that I say Python 3.11, and the reason is because when you select conda, you can first do this, and it won't even install Python, or you can do this, and it will install Python. But right now it installs Python 3.12. At 3.12 is something that is too recent for PySAL. It'll start throwing some errors and say it doesn't recognize it, and so. Then we say Python equals 3.11, which should be good enough for all the packages involved. And you notice what it's done here. It's saying newer version of conda and all this sort of stuff, etc., etc. I wouldn't worry too much about that. And here's what it's going to download just from the very get-go, just to make this environment. And yes, I'm going to download those, or we're going to download them, extracting, wait for a little bit, and it should be done. Okay, wonderful. Now I'm going to activate that environment. Now pay attention down here. We see base, Bernie Hogan, etc. When I go activate like so, now you see it's changed. I'm now in the Geo environment. Now in this environment, I did install Python. So if I type Python right now, we will get a version of it. But if I do something like import pandas, it's not going to know that there's a pandas, because even though I have that on my own Python version, this is now a new one that's inside this virtual environment. So now once we're in here, I'm going to want to first install JupyterLab. Now the nice thing about JupyterLab is that once we install that, a lot of stuff is going to come down with it, including pandas. It's also going to install an ever so slightly more recent version of JupyterLab than what you might have seen from these other videos, which are done using the most recent version of the Anaconda install. And so, yes, I'm going to say yes to this thing and wait for it all to install. Now, still within this virtual environment, you can install the PySAL package either through conda or through pip. Now, as it happens, even though it does recommend installing conda on the website, I've found it to get in a situation where it was getting confused about dependencies, even in the virtual environment. So I found here that pip install PySAL works just fine. Now, you could try pip install PySAL without going through this virtual environment, but you may get some conflicts or dependencies. It may try to update some other things, or it may just get confused and not be able to update it all. This way, I've been able to constrain this and make sure it all is knows what it's up to. Now, this does mean that if you want to install or want to use other libraries, such as, I don't know, transformers, for example, you would have to reinstall that library inside of this environment. Okay, so this is all installed here. Here's a whole series of packages that came down that were useful for getting started with JupyterLab. And now that that's done, we should be able to run JupyterLab. I type that, I run it, and it pops up a whole new version of JupyterLab right here. Now, notably, this was the I'm not actually sure why that one's on there. I think it's because I had rehearsed this in this environment and it somehow remembered. But you'll note that it's running in two different places, and that's not really a good thing. So what we're going to do is we're going to shut this down right here. So make sure that we're not intervening. And localhost, this 8888 one is right there. But now here we are on localhost 8890. So I must have had another additional version from practice running right here. Okay, so here we are. We're back into the notebook, and now when I import this, it should hopefully, cross my fingers, work just fine. Yes, it should work just fine here now. As we see, it's thinking the first time you run it, it's going to be a bit slow to get everything all sorted there, and it should work just fine. Now we check what GeoPandas version we have. We have GeoPandas version 014. Now, they are coming out with a new version of GeoPandas, or they're working towards version 1.0. Depending on when version 1.0 comes out and when you view this video, you might have some trouble with the next little bit of the code. They're getting rid of this, their hosting of specific data sets. Now, there is a way within PySAL to load some other data sets. I believe it's called libsal.example, and then you can check what's available. But it turns out that none of them available are actually maps of the world. And so maybe in a future version of this video, we'll see a new map that's one of the standard ones, like the boroughs of New York that they have in their demos. But for now, we're going to continue working with this and just wait until that GeoPandas 1.0 version comes out, and then this stuff gets changed. Now, for what it's worth, he says you can get the original Natural Earth low res from the Natural Earth site. Now, this is a site for maps and shapefiles. We won't be using this site. We'll be using GADM later on, but it's not actually the same file because it doesn't have the same columns. We have a couple columns that are in this one right here in this natural low res data set, and we can in fact see them right here. Print world columns, population estimate, continent name, an ISO code, GDP, and geometry. Whereas the version from Natural Earth just has the name, the ISO with a different code, the geometry, which is where we get the shape from the map, and a couple other stuff that's not here but more relevant for geography data. Okay, so hopefully you should be able to get that working and have a version there. Now, you can tell that you have a version working, first because, well, we checked to see that there's some columns that came down in our data frame, but also because we can do this. Now, we can plot the world here, and here, let's have a look at a world map. As you recall, I mentioned we have latitude and longitude coordinates, and it's 180 around the Earth either way, and then we go from 90 from the top, and then 90 to the bottom. So here across the middle of the Earth, that's the equator right there, and then here's what's been referred to as the prime meridian, the 0th line, and then the international date line is somewhere around here. You'll also see, look how this map kind of cuts off right here and then loops back right here. These numbers refer to the degrees of longitude or latitude. Now we can, and this is, I think, a really cool part of GeoPandas, is that we can filter it because it's like a pandas data frame. So if we filter down by a single country, so I'm here in the UK, so we can filter down by GBR, and just watch, then it'll just show this this one single country right here. What this also shows is that the map that comes down, this low res map, really is low res. Maybe you can't really tell from here, although when we zoom in, it'll seem like that. But we can definitely tell when we go down here and we see the map itself. Actually, nonetheless, I'll still zoom in a little more. Okay, so we can show a couple things within the GeoDataFrame to kind of get a sense of how they work. So here we are. First, I'm just filtering down this GeoDataFrame to these specific columns right here. There's a few other columns like country name and stuff, and that kind of cramps up the page. So we're just showing these right here. So here we are, name, ISO code, GDP, and geometry. So this is in millions of dollars. So we can see here we have Fiji, Tanzania. I'm not sure the numbers don't seem to be particularly relevant about where they come down. They're not sorted in any order here, like of latitude to longitude or so forth. But importantly, we have a column here called geometry. Now this column contains things like polygons and multi-polygons. Those are specific objects within Shapely, and then if you can define a Shapely object as a series of polygons, you can put it in a geometry column, and then the library will plot it as is. It doesn't have to be the Earth, because even though it's like the Earth, we plot maps at all scales, really tiny maps, maps of cities, and so forth, and each one of them could have their own set of polygons to represent different parts that we want to visualize. So one of the columns that we had there that we didn't see on this one is population, but we have it. It's called population estimate. And then we can create a new column here based on just subtracting one from the other. So this will give us, this is millions of dollars, and this is population estimate. Then we'll have not just the GDP for the country, but the GDP per person. And so that I've created a new column here called GDP per cap. And then you'll notice what I've done down here is I've filtered the map. So we've taken out Antarctica, and I hope that's all right for the people that are in there, but there's really not many there, and no natural populations of humans in Antarctica. So if we cut this off by just removing this from our map, then we should truncate our map at the bottom, which will, zoom it in a little more and make it more visible. It's also worth noting that the map itself really misrepresents or distorts the size of things, but further to the orange metaphor right here, one of the reasons why it's distorted like that is like, how can you make the peel of an orange lay flat and rectangular? And this is why rectangular maps inevitably distort the Earth. We simply can't do it. You'd have to stretch in some way or another, or arrange the segments in some sort of curious way. So there's no really right projection of the Earth, although some are more effective for conveying things than others. Okay, so now let's actually, once we've computed this, then and filtered it down to outside of Antarctica, let's plot and then see here what happens when we plot a column within our data set. And remember, this is within GeoPandas. So GeoPandas knows that when we say to a GeoDataFrame.plot, we mean plot all of the columns in the or plot all of the rows in the geometry column, and then for this extra column, it says represent that within those polygons. So now once we have plotted our map down here, what can we see has happened to that column? It's mapped that column to a color scale. It's mapped it to the default color scale within Matplotlib, which is called Viridis, which is a really neat color scale because it has a lot of nice features such that if you print this in black and white, the colors that are sort of the lighter green are going to show lighter, and the colors that are the darker purple are going to show darker. There's a lot of neat features of that, and I discuss a little bit of the book and point to some resources for that. But the important thing to note is that it's actually a continuous mapping here. And we can see that continuous mapping by giving our map a legend. So I use this here, and this is from actually from the Matplotlib or the GeoPandas tutorial. It says get this toolkit right here to make our axes, and then what we can do with that is then make a legend, but just on the side of the map rather than inside of the map. Now what we see here is that, and you would know this from the Viridis scale, is that it goes from yellow to green to this blue to this kind of purpley blue, or down here. And what that means is that we can distinguish a midpoint. We can see the ones that are either higher or lower within this. But given that it has all this range up here for yellow, where exactly is the yellow on the map? It's kind of hard to see. And maybe if we zoom right in, we can see, well, there's a little bit right there. I guess that's Luxembourg. And maybe we could find somewhere elsewhere on our map. But let's just have a look at that. Now, if we sort our map, or we sort our data frame, we can see what do we have here for GDP per cap, the highest. And then we have Luxembourg, Antarctic, which we've cut off, Falkland Islands and Switzerland. And this is according to our data here, but our data is quite an estimate, so I really wouldn't put too much stock in these numbers. I would recommend that you go and check out the specific GDP per cap figures that you'd find perhaps from the World Bank and from their very thorough set of data that they have available through the World Bank data portal. But nonetheless, what we can see here is that these don't show up very clearly with that yellow. And in fact, if we have just one yellow, it's not really representing all of the distribution very faithfully. And then we have a kind of map that's in a kind of bluish purpley that's a little dark relative to the rest. So instead of just using a continuous value, this is where we can use mapclassify to create a choropleth. Now the choropleth is going to just chunk this up into some divisions and then give the divisions a kind of consistent color scheme. So we can have a look down right here what we've done. I use column GDP per cap again, and now I've used a scheme. And the schemes come from mapclassify. They're schemes for how you might chunk up a distribution. And then here we have a color map. So I added a color map, but if you remove it, then it should do the Viridis map. But let's have a look at what happens when we do that. It was a little bit slow the first time on my computer, but I think it's because it's the first time it used mapclassify and had to compile that. And now we can see we have a color scheme that goes from light to dark, and it has more distinct chunks in there. We're able to kind of identify some kind of variation here within, within Africa, South America, over in Asia. Our legend has now kind of intruded itself in our map, unfortunately, and we could tweak that, and we'll see some ways to do that later. But for now, I just want to communicate the point. And for those curious about Viridis, if we do this, yes, we can see this, and we more or less capture the same. But then we don't simply represent Luxembourg as this one place with this super high GDP versus the rest. We can identify that actually it tends to be part of a large cluster of countries that are relatively wealthy in this metric compared to others. Now, we used mapclassify, but we used it implicitly in here. It was called by GeoPandas through its plotting because it knew that that's what it does. But we can actually import it directly and use it directly. And that's quite handy because we can explore different cut points and just see where it works in our distribution. You'll notice we have these square brackets and these round brackets. That's a way of saying that this includes all of this, and then this includes, up to but not including, or greater than and less than or equal to sort of things. So they kind of all link together and none overlap. You'll also notice that for quantiles, we took all of our countries and then they were split pretty evenly, 36, 35, 35, 35, 36. But we may ask, isn't that a bit arbitrary? Why should we include these 36 most wealthy or most poor countries on this metric? Why not 38? Why not 40? We say, well, we want an even distribution. But it turns out that an even distribution may not effectively communicate a point, but neither does a continuous distribution. So we can find smarter ways to do that, and we'll see those down below. Before we get to that stuff down below, which I'll do with regional data, I want to show first a couple things in how we can manipulate GeoPandas. So this time we're going to download a different data set. It's still from the GeoPandas data set, so it's still going to give us that warning here. But this one's called cities. Now the thing about cities is that it has a point rather than a polygon, and that point is going to represent where are cities that are the capitals of various countries. So now we have here AX worldNA.plot, cities.plot, and if you recall from matplotlib, that what we do is we tend to layer things on top of the map. So if we just do this, and I say worldNA.plot, then we just get the plot itself. But now by putting cities and layering that data frame on it, because it knows through these coordinates here where to locate itself on this map, we'll see those cities like so. And now I said the marker, I use this asterisk, so they show up as like little stars. Color is black, you can change that. Marker size 5, and so forth. All of these are somewhat changeable, but this helps us identify specific points on a map. And, from my own work and my own experience, when you have not just, a couple cities, but a vast number of points, maybe representing, all the photos on Flickr that were tagged on here, or all the Wikipedia entries, or where people are from in a Stack Exchange archive, then these can get quite dense in some way. But that's it, drilling in a little deeper into how you might make a map and make a map make sense. Of course, in order to do that, you have to get that data into your data frame. So below, I'm going to show how to create my own GeoDataFrame by first getting a point. And that point is going to be Greenville, Mississippi. Now, why Greenville, Mississippi? Because it's the birthplace of Jim Henson, and I guess to some extent Kermit the Frog. A bit of a fan. It's as you might recall, a motif in the book. Hasn't shown up for a couple chapters, but here we are back again. So here we see this data frame. There's the latitude and longitude coordinates right there. So now first, I'm actually going to split this up a little bit right here. Just watch this. That's landmarks. Oh, of course I did that. So that's landmarks. And if I go landmarks, what we have here is just a data frame. It's got a latitude column and a longitude column. So this is not going to work as a GeoData frame just yet, but this is going to be the information we're going to use. So in this case, what we've done here is I've first instantiated a GeoData frame. Now if we do that and just make that like so, we're not really going to have much of anything in that data frame right there. we can display it. There's nothing there. So we put in landmarks, which was our original data frame, so it's going to have those columns. And then for the geometry column, what it does is it says GeoPandas points from X, Y. So it's going to take one column, it's going to be the X, and the other column is going to be the Y. And in this case, and by convention, even though it says X and Y, and you might think that X is horizontal and Y is vertical, so why do we have them this way? The longitude coordinates actually represent them along the x-axis. And the latitude coordinates represent the points along the y-axis. So this is our xy, so that's why we have longitude and latitude. So we add them in here, landmarks.long and landmarks.lat. And if I give them a different name, we can say that's .splat, run that again, and then we would, be able to do this with splat. Those aren't reserved words, as it happens. Because you can see now it's it's made that point for us in that geometry column. Okay, now just cleaned up my data a little bit there, and we're back. So once again, I'm going to create another plot, and we're going to see the plot, and we're going to see that point on the plot. Now, once again, we've used world NA, so that's a shapefile that's going to go in the back, and then we're going to plot our data frame, which has just got one point, on the top of it. I use AX here so that the plot becomes the thing that then you get more layers on top of. And so AX up here, and call it again, we could call it AX1, and then we could say our axis is AX1, and it will also plot our point right here. Let's have a look at that, and we can see that's thereabouts where Greenville, Mississippi is, and where Henson was from. So that's just one point itself, but imagine if you were downloading from like a Wikipedia page or a series of them, you could get a whole ensemble of points for things like where is the Eiffel Tower or something. So from this point, I've cleared the kernel of the earlier maps up there, just to show that we can do this section right here independently of the stuff above, just in case you have some trouble at some point with GeoPandas in the release, getting the maps as noted here and in the warning. So first thing that we're going to do is import these libraries again, and then make use of a shapefile. Now, to remind, the shapefile should be in the GitHub archive there, and so if you've downloaded the whole repository, then this will already be in your data folder. So if you want to check out other GADM files, then you can go to their website, gadm.org, and here's what the website looks like itself. It's got maps and data. If you look at the maps, you'll see kind of a lot of images of the maps right here, but actually it's pretty tricky to download. Now, on my computer here with no ad blocks or anything, we can see that actually it's putting a lot of download buttons there. I want to caution against that. What you really want for these maps, if you want other ones, is to either download the data by country or the entire world. And so if we went by country, we can go just like we did with the United Kingdom. Perhaps I'll do my, my home country of Canada. I select on that one, and then you can see here you have these files, and I would download the shapefile right here. It'll come down as a zip, and inside that will be a folder with a variety of different file formats. Now, the one that's in the GitHub right there, which is this version of the Great Britain file, you can see it has maps at level 0, 1, 2, and 3, and so 3 is the most granular, and 0 is just the country level file. Now you'll see here again also we have a lot of shape files, and then this is .shp, but there's also these PRJ, DBF, CPG files, and these generally come down with a shapefile, and you won't have to load them directly, but the program might be might have a bit of an issue if it doesn't find them. In the example here of this the world map, and they point it out and say, if you can't find it here, then you can go and look for it on this website. That website being the Natural Earth Data right here. That similarly comes down if you click on this, and you'll see here it also has the SHP, SHX, these sorts of files as well. But in both cases, if you were to load it directly, you just need to load the shapefile, and it will look for the rest. So that's what I've done here, and we've loaded this, and we can plot that right there. And first we're going to see this plot at the at just the level 1. Now level 1 in the United Kingdom. I mean, I said a country, but actually we're referring to the UK as a kingdom, the United Kingdom of Great Britain and Northern Ireland. And within there are 4 countries. And so these countries here, Scotland, Northern Ireland, Wales, and England, are shown on this map. And that's at the level 1. But if we want to go a little more granular, we can load up the level 3 map, and that will show all the counties across the different areas. And you can see there it's much more granular, and if we zoom in, also because this is SVG, when it's zoomed in, it's all pretty nice and crisp, and much better than the one we saw above, which, I don't know, kind of looked like the logo for the 2012 Olympics. Is very, very blocky and so forth. Let's have a look at what columns are available within this right here. Now, this is the GADM file, and so it comes down with a data frame. And the data frame has these details like GID, name, and so forth, and that's at the various levels. So we can sample some of those right here and look at the name of the place, and name 3 will be the most granular name. So I've just sampled 5 here, I guess a random state of 7. And you'll see that the first one there is Nottingham, the bottom one there is Anglesey, and they're both, they're from different parts of the UK here. Level 1 shows that these are from England, this one from Wales and then Scotland. And then here's the level 3 name. That might also actually be the name at level 2, but you can investigate that in the columns yourself. So now, while it's useful to be able to just map a map, what's really relevant, of course, with this is that we're using a map as a sense of place where we map on other data. And so the data we map could either be the presence or absence of a point, or it could be something for a particular region. We saw the regions above as choropleths, and here we can see regions in what we're going to do and use some COVID statistics. Now, these were statistics that were collected for the first year and a half of COVID in England, coming from Public Health England, and they were put together by the OxCOVID project. And this project consolidated a lot of data from places like the Google Earth mobility data that was shared in an anonymized format, mapped to weather data, and mapped to things like when the various lockdowns and such happened across the world. So it's a pretty complicated data set to coordinate. It may or may not be available when when you're watching this video, because I know that it's not necessarily a permanently public-facing thing. But there was a version of it they would pack up as a zip file and make available on the web, and those probably are still available right now. But I have one of them available, shared from the OxCOVID project in the GitHub archive with their permission, and it is public data. So we're going to have a look at that data and then try to merge it in with the GADM data. Now, again, if you've downloaded the data archive in the repository, this should be available for you just in your data directory within the repo. And you'll also notice here that it's a .bz file, so it's a compressed file, and it's a CSV. But Pandas will read the compressed file, no problem, doesn't need to deflate it first. You can just keep it in that format. Now, if we look at the length of it in terms of the number of rows in the data, we'll find that it's actually pretty large. It's got 260,000 rows. So the 260,000 rows represent different observations for each of these level 3, well, thereabouts for each of these level 3s, such as Nottingham or Torbay, and for the days of the year. So there's it's going to be a lot of redundancy in the data set, and we really just want to, at this point, look at one snapshot at one day. So whatever the last day was in the data set, we'll have a look at that. And so we can have a look at the data here, and I've looked at the first row, but with 0 there. And this is from 2021, and this is in Gosport. And so here we have, these were some of the statistics that we have available up to this point on things. And so this was number of confirmed cases and number of dead. So, I mean, it's, it did hit England as it did hit a lot of places, hard. It was a really, unfortunate pandemic, as we all would recall going through. But what's notable here is that we can have a look at some of these statistics across the different regions and think of that as a way to merge in some data. Now, I also use this data set in a way, and I didn't sort of like pre-chew it or clean it up for people, because I wanted to show some of the experiences of getting data from, out there on the web and being able to wrangle it outside of, Stack Exchange and so forth. Here's one interesting example of this data set. And what we see here is the GID Now this will be the way, this will be our key for linking to the GADM shapefiles. But it's here, it looks kind of like a list, doesn't it? But it's not actually a list. If we go have a look at this down here, say COVIDF.loc0 there, and we'll put in GID. Look at that, it's got some quotes on it. So if we put a type around it, and so we can see it's a type of string. So that means we want to change that back into a list. Now, why do we want to do that? We'll see once we change it back into a list that not every one of these rows just represents one county. Some of them represent multiple counties. And so that could be a bit of a complication for our data. We're going to propose I'm going to propose a simple solution to that here, but you would want a more sophisticated solution if you are, really doing this data to crunch the numbers, certainly for proper estimations of public health statistics. Yeah, and what we've loaded here is the abstract syntax module. So what this is going to do is it's going to take strings and turn them into some other value that we know. So it knows that this is a list, so we can convert it into that. Now, before we do that, I wanted to highlight this here, and this is from how I deduced this in the book. We can see here, if we just filter down to the first date, or the most recent date, as it happens, and then create a new data frame with that, that's the one that we're going to use. But now look at the length of that new data frame, and then look at the length of the shapefiles. Now, the shapefiles I had to reduce to England because they use the entire UK, but this is statistics from Public Health England, so it already is reduced down to England. Now, in the CDF one here, the COVID data frame, we've got 315 rows for that day, yet we've got 326 rows in our shapefile, so that's 326 different counties at this level. So what happened there was indeed the GID, sometimes it refers to more than one county. So in order to parse them, I've used the abstract syntax library right here, AST. And what we'll do with that, if you'll see down in the code here, ast.literaleval, it reads that as if it's literally just like some Python data. In this case, it'll figure out it's a list, and then turn that and transform it into a list. It says here you can only convert the data once. If you try to do it a second time, that's because I am not creating a new variable column and putting something else in there. I'm using the same column called GID, and the reason is because that was meant to be as a list column. It was just exported as CSV, and so because of it, it exported this list as a string. So if you'll notice what I've done here is I've also printed the length of gid.sum. So CDF GID, if we see here now, for the COVID data frame.gid, there's all of them. If we take the first one, it now looks like a list, doesn't it? In fact, it's the type is a list. So if we have a list here and we do a sum for that, what it's going to do is it's going to put them all together as a single list right there. And so from all of the different columns across all of them, and so that we look what the length of that is, and it's 326, as it should be set up there, which is good because that is indeed the number of administrative units in the GADM. So that means we now have enough. We have one GADM key for the rows in our database, but as it happens, they're not evenly distributed. You'll notice I did that above with this explode command. Because we have this in a list where sometimes we have two entries in a list, if we explode, what it'll do is it'll make one for each entry in that list. And that's why we can see down here the length of that list now is 326, just like the length of the shapefile. And I also, I sum up all the scores for the confirmed cases in the new database, in the new data frame over here and the old one, just to make sure that it's even. So we have just as many cases across the whole data set, but they're now more properly distributed across the different counties. And down below, I calculated a thing here called the case fatality ratio. It is somewhat contentious because it requires us to have an accurate number of the cases in order to estimate that. In the book, I point to some work where people are talking about the CFR and give it a bit of a critical look. But nevertheless, it's a useful statistic here because of a phenomenon with the counties. In this data, we don't have, or in this specific table, we don't have population. So what's going to happen if we just report the number of confirmed? It'll really show just a reflection of the population. Not exactly, but indeed, if one county is, in the city of London, might have, tens, hundreds of thousands of people, it's likely going to have proportionately at least more cases. So by using the CFR ratio here, it's a little more towards a proportion, and instead now it answers, or it asks, or at least now instead it suggests a research question. If the case fatality ratio is higher in some areas of the country, does that mean that COVID hit them harder? Now, even if the case fatality ratio is not exactly precise, this may give us some intuitions or places to look for that indeed would seem to be hit harder. Now, if you were planning on where to place a hospital or put some hospital funding, this might be one clue that you could put towards that. Now, I'm not claiming that as a fact strongly here from this work. This is really data that we're using just for the purposes of being able to merge in some data. But these sorts of questions would be plausible through this work. While the map itself is not going to be, as sufficient relative to a statistical analysis, it can perhaps also suggest some patterns in places. But in order for those patterns to be reasonable, we're going to have to make sure that our data is properly normalized. So here we are. We create the CFR, and I'll just have a look at that. Some statistics of it. The average rate here is 2, so that is in the first year and a half of COVID. Indeed, of those that reported it, on average, 2% of them had passed away, unfortunately. And the median of that is, pretty close to it as well. So while there might be a bit of a heavy tailness on this, because the mean is higher than the median, it wouldn't be too extreme. Now we can plot that as well and have a look at the distribution. I used a histogram here. I didn't make it too granular, but we can really see that there's, kind of a peak here and then a little bit of a long tail. Now, whether that long tail is due to reporting difficulties or whether the these places were especially hit hard, that would be kind of the next step in this analysis. But it is worth noting that some places had almost double the case fatality ratio of the others. Now, I mentioned above that we had imported the mapclassify package, and it's a pretty neat package for cutting up a distribution. We had used it to make some choropleths, and we'd used quintiles, so we were able to split it up into sort of even chunks. Now, down here I give a demonstration about how splitting it into quantiles might not be the best idea, and I give that a comparison to a thing here called Fisher-Jenks. Now, whereas in the book we're going to show it just shows the whole diagram. I'm actually going to show this in pieces here first. So let's start this, and we'll have a look at the case fatality ratio. And here's what happens if we cut it up into quantiles. This becomes the lower quantile, and then we have 2, 3, and 4 in this really narrow band of case fatality ratio from 0.6 to 0.8 and 0.18 to 0.22. And I don't think they really represent the qualitative differences that we can see as being evident within this distribution, with these being quite a low CFR, and these right here within much more of the expected range. There's much more of them here, and then maybe a chunk there and a chunk right there. So now what Fisher-Jenks does is that it classifies the data not in like strictly even groups, but tries to keep the groups broadly even, while at the same time representing substantive changes in the distribution shape. So if we look down here at Fisher-Jenks instead, we can see that we've kind of neatly chunked this into like really low CFR, 2 groups of kind of the average CFR, slightly higher than average, and significantly or perhaps substantively higher than average. Whether it's significant, we'd have to investigate a little further than this. And so if we layer the 2 of them on top of each other in this chart, we can see here why Fisher-Jenks might be considered a much more sensible way to represent the different sort of chunks of the distribution. Now we're going to use that and apply it to a map, but I'm also suggesting here that it's not just for maps, even though it comes from the mapclassify package, but it is a really nice algorithm for splitting this stuff up if you have a single distribution that you want to classify. So down here, you'll notice what I've done is I'm going to merge in this CDF-EX dataset. Remember, that was the GeoDataFrame dataset, but then we exploded it so that we have just enough rows for all of our shapefile. Left on GID, right on GID. So you can see there we're using different keys in the two of them, and we should be able to link them together still no problem. I didn't give any feedback to that one, but we can see that feedback down here when I plot the map. Now, you noticed before when we had a legend, it was kind of occluding over the map. I've used this bit of code here, set bbox to anchor right here, and what it's done is 0.5, and 1.5 is over here down and down this much, so it's not actually over atop the map. And you can see what might happen if we do that instead. And also down right here, we have these nice qualitatively separated groups. And we can see really here over in the east of England that we had a lot of really unfortunately high case fatality ratio. Now, this was a year and a half in. I don't know if it really panned out this way over the course of the event. It'd be really worth considering and reflecting on this, analyzing a little further. But we can see that there does seem to be some substantive differences across England that may be patterned, if you will, by the different region. We might say that that's what's called spatially autocorrelated, but we'd have to use a little more sophisticated stats to do that. But fortunately, now that you've been able to merge in some data and some geographical stuff, these sorts of merging could really be at your disposal. Now, you notice, interestingly, for most of this presentation, I didn't actually go through this within the slides. Instead, I veered more towards the code for this. Now, the slides are available through Sage if you want to check them out yourself, but I will just sort of skim through them here along the way. To review, here's a data frame that we can put together. Here's a choropleth map, and that's how we can split this up into meaningful divisions. We can also take those maps and put them as points on this, and we can see capitals of various cities and places here around the world. We can create our own data frame. Now, if you'll notice down below, for this particular one, we first created a data frame with this lat and long column. Could be anything, but that's what we called it down here. And then we made a GeoPandas points from XY column of that. Now, in this case, it was only one row of data, but this will work if you have many rows of data, and you could collect in geographic data with lat and long coordinates from a variety of places. You notice we had these shapefiles here, and at first I showed the default map, and then later on we used the GADM, and in the GADM one you can see it's much more high resolution here, certainly by comparison. We showed how to map some stuff in the subnational level, and for that, we used GADM, introduced the GADM data, even a folder of it, and then we can see that it had this code here, which signifies the actual key that we're going to link across data, and that we were able to link that with other stuff, such as in this case COVID data. We used OxCOVID data and calculated a case fatality ratio, and then I showed over here two different ways for us to represent it, one by quantiles and one by the Fisher-Jenks algorithm for splitting up a distribution. And I, of course, suggested that Fisher-Jenks is probably more representative of this than the quantiles was. You can see how this wide range of the fifth quantile, despite the fact that this is probably a much more substantial difference than this over here. And then finally, merging that together, we can make our own maps at not just the national level, but at the subnational level. So in summary, the chapter focused on mapping data. First we talked conceptually about the challenges of having our data having to have latitude and or latitude and longitude coordinates to map over there. Certainly showing how maps as projections don't seem to be entirely ideal. Use the metaphor of the orange and trying to peel an orange. How do you map that and flatten it out without breaking the orange? It's pretty challenging. Nevertheless, we use that coordinate system and we're able to map things, and it's not so bad when we zoom into like a country or certainly a city level, that warping there. And regardless of these levels, we can do that with GeoPandas. GeoPandas requires us to use a data frame that has a geometry column. It's in a thing called a GeoDataFrame. Now that geometry column can come from or be exported to, I believe, a shapefile. And when we download shapefiles, they come with other files as well, but we load the shapefile, and then that's what we use in order to do our mapping. So now we have mapping and some spatial stuff that we can put within our toolbox of things to apply, towards a social data science framework. So we can represent the data so we can represent space in a number of different ways. We can rank distributions of space on a bar chart, looking at the proportions of something that's happening. We can do that in a bivariate way. We can do it in a scatter plot, but we can also do it on a map. Similarly with varying intensity, points on a dots, or choropleth type things with different color bars. So now I had mentioned the World Bank's data platform a few times, and it's partially because it's it's very extensive, and also because it has ISO codes for countries that can be easily mapped onto these sorts of data frames that you have here, such as the Natural Earth Low Res one, and you can use the ISO A3 code for that. While the World Bank's data is very extensive, it's not without some sense of contestation, and it's also worth digging deep into how different places arrived at some of these numbers, when it could be anything from the amount of greenhouse carbon gases that it produces to what is the reliable population, at any given year. And whether we visualize that on a map spatially, or whether we do something like use a scatter plot or a histogram, we might end up revealing different things about the data. Now, as an exercise, something you might do, and as alluded to earlier with the plotting of a single lat-long coordinate, you may first start to consider doing this by hand with a few cases, and then thinking about how you might scale this up in some manner. So in a simple way, think about 10 musical artists. 10's an arbitrary number, but imagine them being able to, look up where they were born, just as, I did there with Jim Henson. So if you go to the Wikipedia page for that place, you can get the lat-long coordinates, and you can build a GeoDataFrame. Do you notice any patterns? Do you notice that those musical artists are from a specific place? Are they concentrated within a country or within a specific area of the country? Were they all born in London, or were they all born in rural Canada? There might not be a pattern there, but you start to get an intuition about where your tastes may have come from and how those people made their careers. Scaling that up even further, you'll be able to start to see more broad spatial patterns about maybe the flow of cultural tastes or funding towards music or so forth. Beyond that, I think this exercise is useful in the sense that it does get a bit repetitive after a while, but you start to get a sense for, is there a regularity of the pattern that you can find? Then scaling that up, you might think, well, how can we look for all musical artists? Or all musical artists, find the artists themselves, find out where they're born, get those latitude, longitude coordinates. And then you start getting towards a pipeline. Now, this is near the end of the actual data science chapters in this book, but it's only the beginning of a journey on doing this sort of work. And I suggest this particular exercise because I think one of the most useful places to go after here is to think about your work as a pipeline, not merely as a series of skills that you've developed here, but then how do you stitch those skills together so that you can scale up into increasingly ambitious or interesting work to help you represent the world around you. So with that note, I just want to thank you for checking out these chapters, following along in the book, and I hope it was enjoyable for you, and you've learned as much as I have in writing this, and continually updating it as happens on the GitHub. So thank you for watching, and have a great day.